Hello, everyone. My name is Daniel, or Zihuiwen. Yeah. Today I'm going to talk about our work on improving role models with synthetic critiques. So this was a research project that I did during my internship at Cohere, and a joint project with my colleagues Fraser, Max, Phil, John, and Matthias. And a little introduction about me. So I'm currently a PhD candidate at the University of Oxford at the computer science department, and I mostly do research on NLP. I really appreciate the opportunity to be here and give a talk to everyone at CAMEL, and thank you so much for inviting me. And yeah, thanks for joining. So I could probably just go on. Okay, so a little bit about the outline of this talk. I'll first talk about the background before introducing the work, which mostly centers around reinforcement learning with human feedback and role models, and then the role of role models and their challenges. So afterwards, I'll talk about the motivations for enhancing role models with textual critiques, including the advantages of integrating textual feedback. And then I'll move on to talk more about the methods and experimental setup, which includes the training objectives and data sets and models. And in the end, I'll explain the main findings and analysis and discussions. So please feel free to ask any questions if anything is unclear. So a little bit on the background of RLHF and role models. The current generation of large language models, including Claude, Gemini, GPT families, they are training multiple stages. And after being pre-trained on trillions of tokens, they then enter the RLHF, or reinforcement learning from human feedback loop, where this is when the models are trained to align with human values and produce outputs that are desired by humans. So I have a screenshot here from the paper Instruct GPT. So I'll quickly introduce the 3 steps that are central in the RLHF framework. In the first step here, it is called the instruction fine-tuning or supervised fine-tuning stage, where people collect a large amount of SFT data of the format of input and output pairs, where the input will be a prompt. For example, here it's in the screenshot, it says, explain the moon landing to a 6-year-old. So given this prompt, there will be an associated output pair, that's output completion, that's labeled by human. So here it says some people went to the moon. So there are many examples of this format of data pairs, and the models are trained to, when given this prompt, produce outputs that imitate human behavior, basically. So after the training ends, the model at this stage hopefully is going to be able to produce answer instructions and follow instructions, etc. So in the second stage, in the second step, it is the role model training step. So in this step, a separate model called the role model is trained, and the goal is to use this model to predict human preference. So specifically, in this step, a different data set is collected in a different format, which is called the preference data set. So this data set has a different format from the previous step. So for example, here they have the prompt, explain the moon landing to a 6-year-old, as well as a few model completions that could be produced, those outputs could be produced by different models, and they all try to answer this prompt, but they might be of varying qualities. So for example, the first option A completion is explain gravity, which is less relevant. And the second completion is explain war, which is even less relevant. And then the C option is probably a bit complicated for a 6-year-old. And then the D option is the desired one that kind of explains things clearly to a 6-year-old. So given both the completions and the prompt, the output here would be a human-labeled ranking of the completion pairs from the best quality to the worst preferred by humans. So in this format, the role model, which is usually pre-trained which is usually initialized from a pre-trained language model. It takes in both the prompt and completion pairs, and it will produce a scalar output that assigns the highest value to the most preferred one ranked by humans. So the idea is that by the end of it, the real model can produce a scalar output that accurately predicts human preference by assigning it the highest value. So the end goal is to have this model that represents human preference by the end of this step. And then in the last step, it is when we take the trained rule models and use them to actually fine-tune the language model from the first step. So usually reinforcement learning algorithms such as PPO are used to update the policy and then train the language model to produce outputs that would maximize the rewards from the second step real model that's being trained. So this is the overall framework for RLHF. And in this talk, I'm mostly going to focus on the second step, which is the real model training step. And that's also the main focus of the research project that I worked on. So I'll only focus on this step. But the idea is that once we have a strong real models, then the performance could be transferred to the underlying language models when we do a PPO update, for example. So yeah, as previously mentioned, real models, they play a critical role in aligning language models during reinforcement learning from human feedback. They assign a scalar score to predict whether humans prefer one text over another, and they are trained and evaluated on preference data with the following format. So I give an example of similar to the previous example, but here's like in more detail. So given the prompt, suggest a suitable card game for a birthday party, there will be 2 completions. Those could be model generated by different models. And then the first completion says, Cards Against Humanity is a great card game. It's hilarious, that involves answering questions and filling blanks with funny blah, blah, blah. It's easy to learn. And the second completion is a few activities could be scavenger hunt or lingual competition, which are actually both not card games. So a human would assign a preferred option to be the first completion. So that's why it's called the chosen one, and the second one is the rejected one. So the idea is to train the real model to assign a higher score to the first chosen pair. So here the real model is trained to produce 2 scores. For example, if it produces a 0.57 to the chosen one and a 0.23 to the rejected one, then that will be a win situation because the reward for the preferred one is higher. And if it does the opposite, then it's a loss. So during evaluation, people usually just evaluate the models and then on a test set and then count the number of wins and use that as a proportion of accuracy as a metric. So here, I'll just move on. So, however, there are some problems with the real models and RLHF. Understanding how RLHF processes align with human preferences is challenging due to a lack of explainability and interpretability in real model training. So, for example, the preference scores annotated by humans are noisy and subjective. Sometimes a pair that is preferred by a human might be less preferred by another human, for example. So this will result in low inter-agreement rate between the annotators. And second, real models can overfit easily and fit to superficial features in the training data. So for example, if the preferred option is always the longer one, then the model might pick up this trait and just fit to prefer the longer completion, which is not really desired. And last is that obtaining preference pairs for real model training could be expensive. So existing preference datasets are small and limited to specific tasks such as summarization or code. And it's usually quite expensive to have humans annotate the pairs. Considering those challenges, we propose augmenting the preference data with model-generated and natural language critiques to overcome the above limitations. So what are critiques? They are natural language feedback that break down various aspects in the response, such as instruction following, correctness, and helpfulness. They're kind of give a they kind of illustrate like the weaknesses and strengths of a pair of input-output pairs in a more interpretable, accessible, and cost-effective way. So I will show some examples of critiques in the next slide, but to show just the template we use is a very simple one. We follow previous ultra feedback. So this was a word that also try training models with similar data, but we kind of kept it very simple. Given the user prompt and the chatbot response, we just have a simple, please provide a critique of the response in one short paragraph. The critique should be concise, specific, insightful, and to the point. And aspects you should consider are helpfulness. A good response should be closely following the answer the user's request, and correctness. So we just use the very simple prompt, and here we show some examples. So it's the same pair that I showed in the previous slide. We just augment it with critique. So we generate 2 critiques individually, prompting large language models. So to be specific, for the chosen pair, the critiques will say, while the recommendation is helpful and suggests a game that is popular for its human ease of play, it may not fully consider the audience diversity and sensitivity, as it might contain potentially offensive material. And for the second rejected one, it will say something like, it's factually correct, however, it didn't address users' request for a game that for birthday party, instead offering alternatives in the form of physical activities in games. So the idea is that they break down the various aspects in the original chosen rejected pair in a more interpretable way, and then they also kind of lay out the features more clearly and enrich the text to provide more features for the role models to learn. And hopefully this will result in a more robust training, and also easier to fit, given the extra features here. So yeah, and then the rest will be the same. We just take rule models and additionally condition not only the prompt completion pairs, but also on the critiques. So to be more formal, we compare with the baseline of just normal vanilla reward model training without any critiques. So in the literature, this is usually done in using a binary ranking loss. So here is the loss objective. We train over a data set of D, sample examples of the form x, y plus, y minus, where x is the prompt, y plus is the preferred completion, y minus is the less preferred completion. And then inside the log term, first the r theta of x, y plus is the reward scalar score for the preferred option, a preferred completion pair, and the r theta of x, y minus is the score for the less preferred completion pair. And the theta is the trainable parameters here, initialized from the pre-trained large language models. And additionally, there will be a margin term MR that denotes the preference rating. And large margin will be used for responses with distinct ratings. For example, when the difference is big, humans strongly prefer one over the other, and the small if they're similar. So the idea is to minimize this loss by maximizing the difference between the score assigned to the preferred one and then the score assigned to the less preferred one. Sorry. And so we propose just simply concatenating the critiques in the second objective here. We just concatenate the textual critiques after each response. We generate them individually and just concatenate them individually after each response. So everything else stays the same. So it's quite this minimum change here. And then for the experimental setup, we have a training set of 5K preference data of open-ended conversations between user and chatbot with human labels. So that would be a human, given the prompt, like maybe a question raised by a human, there will be 2 completions generated by chatbots. And then the label will be one completion will be better than the other. And so for the evaluation set, we have 2 open-sourced rule model benchmarks. One is the rule bench, which has 4 categories. For the chat subcategory, it's open-ended chat prompts, and chat heart is an adversarial data set where they design the prompts and completion pairs to be specifically tricky for the language models to understand. And then the safety questions, and reasoning has some math and code prompts where, for example, the word completion for a code example will have like bugs, whereas the preferred option will have no bugs. So that's the first benchmark. The second benchmark is Panda-LM, which is another set of examples from self-instruct and labeled by 3 human annotators. So we do experiments ranging using the critiques generated from a pool of 6 models. So we have like models from different sizes: Llama 27B chat, Llama 27B chat, Mixtral 8x7B instruct, CAMEL-R plus, and GPT-4 turbo. And then so they're all instruction tuned and post-trained, so they know how to kind of answer instructions accurately, clearly. And the second thing we vary is we vary the checkpoints to initialize the role models from. So we have 3 pre-trained checkpoints: Llama 27B base, Command 35B base, and CAMEL-R 35B. So they range from weak to strong, in a sense, and we want to know whether that also influenced the performance. So we train role models from one epoch on the training data, and then make sure that the training and evaluation set match, meaning that the test set also has the critiques augmented, so just to match the training setting. And the result is here. So in this plot, the x-axis is the role model pre-trained checkpoints, ranging from 7B Llama to B base, 35B command base, and 30B CAMEL-R from weak to strong. And on the y-axis is the reward bench score. So in the 3 groups here, the ones on the left, the gray ones, are no critiques baseline, and all the other ones in different patterns and colors are augmented with critiques generated by different models. So the first observation is that high-quality critiques improve role model test accuracy. So we see that strong critiques such as GPT-4 Turbo, the blue one on the right, they improved scores on role models starting from the first 2 groups here, the most significantly, and followed by other weaker models. And weaker critiques such as Llama 27B chat could actually be detrimental. And so this just shows that the critique quality does match. And we think it's because if the quality is not really desirable, then that would actually introduce more noises and like worse features to fit to that confuse the models even more. So yeah, the second point is that critiques are more effective on weaker role model checkpoints. So here we see that the 35B command are like the ones on the right, the most right hand side. They're kind of less, like critiques are less effective here, and we think that this is because the starting checkpoint, the 35B command R, is already quite strong and it's quite optimized and post-trained. So like adding the critiques might actually be a bit like over distribution for this model, but actually scaling up might have a difference here. But here we only have 5K, so that's probably why we see this here. And we also try scaling up. So on the x-axis, we have training examples of sizes ranging from 5K all the way to 200K. And on the y-axis is the same rule bench score. So the 2 lines here are no critiques and the CAMEL-R plus critiques. So also in the background we have the 4 dashed lines. They are the 5K, just augmenting it with 5K critiques. So it serves as like a reference before scaling up. And we see that increasing the number of training samples increases test accuracy, both with or without critiques. So both lines here are going up. And then using synthetic critiques enhances data efficiency, particularly in low data settings. So we see that the marginal benefit of critiques decreases with more data. So here at 5K, the gap is the biggest, and it kind of gradually decreases over number of trained data. However, yeah, we're also interested in how many no critiques example is a critique worth. So we kind of look for the intersection between the dashed lines and the gray no critiques lines here. So roughly 5K command R plus critiques is 90K no critiques, and even 5K GPT-4 Turbo is results in a better performance than using 200K no critiques. So that again says the critique quality matters, and using 5K can surpass 200K no critiques when using the high quality critiques. So and following that, we also have some analysis by breaking the task down by categories. So this is the same rule bench performance, but we just plot different plots for the different subcategories. So for the chat, after scaling up, we didn't see much influence from the critiques. But for the reasoning and chat, which are more difficult, we see a consistent gain in reward score. So the reasoning one has like slightly higher one at the end, and then for the chat hard is an adversarial one, and we see less drop in the performance in long term, like in scaling up for the critiques. And we hypothesize that they are more effective on the more challenging tasks because, for example, the reasoning for the reasoning task, the critiques are kind of like chain of thought style format, and they're chain of thoughts for the real models. So they're informative real models to kind of judge the results based on those extra thoughts. And then for the chat hard, we think this is because the critiques have the extra features laid out, and then they might point to like the more crucial features such as instruction following and correctness, which models could fit to, and then they will be less likely to overfit to like length or other superficial qualities in the data set. So yeah, those are the main findings. And in conclusion, we propose an accessible and cost-effective approach to improve real models in RHF by enriching them with synthetic critiques. And the benefit of critiques is greater when they're of high quality, especially for real models initialized from weaker pre-trained models and in low data settings. And please check out the paper for more details. And for future work, we would like to train the language models with the critique enhanced real models to see if they actually transfer to the underlying language models, and then potentially to improve reasoning abilities, since we saw some performance gains with the reasoning tasks. And also the critique qualities could have a big impact, but we did see some hallucinations, so might help if we improve the critique generators. Yeah, thank you. That's the end of my talk.